Okay, let's talk about accumulation and net change. The net change theorem, which I don't care if you know the name of it, just as long as you can identify when to use it and how to use it. This is something we've actually already talked about. Uh, the net change theorem essentially is part of the fundamental theorem of calculus where the antiderivative from A to B, or the area from A to B, you find the antiderivative, plug in B, plug in A, and subtract. So there is the basis of your net change theorem. What I'm going to do that's slightly different is I'm simply going to take this f of A and I'm going to move it to the other side of the equation over here with this antiderivative, which would give me f of A plus the antiderivative from A to B of f prime of x equals f of B. And the reason I did that is because there are going to be times where you are given a rate of change or a derivative, and you're given some initial amount, and then it asks you to find the amount at a later point in time. And this is the format you're going to use. When you're given the initial amount plus a rate of change, that will give you the final amount. There. So we start with the initial amount, which is right here. Plus the net change, which is here. And that will give you the final amount right here. Pretty simple concept compared to some of the other things that we've done lately. So a few examples using this theorem. And I'm going to give you a simple one first. I'm asking you to find f of 4. You're given f of 1, which is 2, and you're given the rate of change. Now you could find the antiderivative plus a c and use this condition to solve for the constant, and then plug 4 in to get your function, or the value of f of 4. However, since I have the rate of change and the initial condition, I'm simply going to say f of 4 is going to be my initial amount plus the change from 1 to 4 under the derivative of f. So f of 1 was 2 plus antiderivative from 1 to 4 of f prime, which is 3x squared plus 1. And then we'll evaluate that antiderivative. And there you go. Pretty easy antiderivative, so I went ahead and worked that out real quick. And you end up with a value of f of 4 being 68. Sometimes the setup is not quite as explicitly clear, and that usually happens when there's some kind of application to the rate of change. So here we have the initial position of an object being 4 meters, and I want the position 3 seconds later. Let's see, so initial position, that is your position at time 0. So s of 0 is 4. The question is asking for the position 3 seconds later, so I want to know what s of 3 is. And we're given the velocity, which is also the derivative of position. And so if I have an initial condition, I want some final amount, and I'm given the rate of change, then I could say that s of 3 is going to be whatever my initial condition is, s of 0, plus the area from 0 to 3 under that function 2t plus 1. So that would be s of 0 is 4 plus, and then this antiderivative, t squared plus t from 0 to 3. And we'll evaluate that to get our value for s of 3. There we go. Okay, one more problem. And this one is modeled after a question on the 2013 AP exam. I altered it a little bit to make it a little bit less cumbersome than what was on the AP exam in 2013. So we are given the rate in tons per hour. So I'm going to pay attention to units because every now and then they get evil and they flip up units on you. So the rate in tons per hour that unprocessed gravel arrives at a gravel processing plant is this. Now this is a rate. Pay attention to that. Now I know it only says G. It doesn't say G prime. But this was defined as a rate. So we're given the rate that something changes. The plant opens at 8 and has 500 tons of gravel at that time, that is your initial condition. So at 8 a.m., we have 500 tons. So there's your initial condition. And the question is asking how much unprocessed gravel is in the plant at 11 a.m. Now, in this case, what you may be tempted to do is say the initial condition is at 8 a.m. So my amount, we don't have a function for the actual amount. We have a function for the rate, but we don't have a function for the actual amount. So I'm going to do this. I'm going to say let's let A of t equal the actual amount of gravel in tons. So I'm going to define that function. Since they did not define a function for the amount, I'm going to have to come up with one on my own. And what I was saying just a minute ago is you may be tempted to say that my amount, the initial condition, at 8 a.m. is 500 tons. I don't want to do that because I would rather let my initial condition be at my initial time, which I prefer to use 0. So instead of saying A of 8, I'm just going to make the declaration that t equals 0 is 8 a.m. And if I want the amount of gravel at 11 a.m., then that's my amount 3 hours later. So 11 a.m. is going to be when t is equal to 3. And so the question is asking for A of 3. So we have some initial amount. We're looking for the amount later, and we're given the rate of change. Well, I'm going to set up that change theorem, the net change theorem. So my amount at time 3 is going to equal my initial amount at 0, plus, and then I need to measure the change from 0 to 3 under the rate, which they defined as g of t. So I'm going to be lazy and just write g of t instead of writing all of that. And this problem was a calculator question, so I'm actually going to go to my calculator here and punch this in. I will go ahead and plug in 500 here for a of 0. So a of 0 plus area from 0 to 3. Boy, my integral signs are crap right now. And I'll punch this in the calculator really quick. All right, so I punched it in the calculator and I made a slight error. And this is one of the few times that you can kind of gauge reasonableness, reasonability, whatever. I punched it in the calculator and I got an answer of 401, which I didn't like because the problem says gravel is arriving and I started with 500. So how did I end up with less than I started? And I made a very simple, easy to make mistake, and I just forgot to add the 500 at the beginning. So if you look at my setup here, I just did the antiderivative. I didn't do the plus 500. So I really need to do 500 plus that antiderivative, which would give me 901, whatever. So there's our answer for this problem. And always remember to include units when you're answering a question like this. So how much unprocessed gravel is in the plant? We started with 500 and we added another 401. So there are that many tons. And then also remember in AP calculus, you always round to the third decimal. It wouldn't be wrong to include more, but you have to go to at least 3. And this is one of those cases where they would have taken 901.664 following standard rounding procedures, or 901.663 if you want to go the truncating route.